Well, at this point, I've all but officially become a book review channel. But hey, that's because I'm working a lot on my thesis and my research, and that is a good thing. Maybe not for you viewers, but okay, last video was a little bit lackluster. I talked about some books I didn't absolutely love. We're gonna get into some good stuff today. And probably the next couple videos are going to be books I'm excited about. So first, I'm probably going to make a terrible, distasteful thumbnail about this one involving recent events, but the first is a hard copy of Hardy's A Mathematician's Apology. I actually picked this one up for free. I'm pretty sure I would have just, if I wanted to read this, I would have read it online for free, but hey, free hard copy, sure, I'll take it. So some of you might know, I guess in some sense, if I recall correctly, this is the famous mathematician Hardy, G.H. Hardy, I think it is, who interacted with Ramanujan. I don't want to say discovered. I guess he kind of did, but interacted with Ramanujan, sort of brought him, over and worked together with him to make his, ideas more digestible to Western audiences. I guess this is his sort of grappling with what it means to be a mathematician, and is it moral, to be a brilliant person. Not that all mathematicians are brilliant, but Hardy certainly was. But even if you're a stupid mathematician, you've got a certain amount of intellectual competence, right? And there's a lot of good that could be done in the world with that intellectual competence. And so, you then wonder, well, should I spend my time trying to work on the Riemann hypothesis, which is on the cover, or could I use that intelligence to develop something useful to the world, go into medicine or some new technology that's going to save lives or something. And I grapple with this, I think, as well. And I think too many people dismiss it. Too many mathematicians dismiss it. Well, probably in general, too many people too quickly dismiss the immorality of their own fields, whatever it may be. Well, because who really wants to take a really deep inward dive and come to the conclusion that something they've spent their whole life on is not the most morally justified way to spend their life, right? So you might not even want to give it an honest thought. But he sort of goes into it and says, basically, hashtag sorry, not sorry for being a mathematician. Decent book. Actually, here's one. I wonder what this book, I really wonder what I would think about it now, actually. I'm interested. Maybe I'll take a closer look at it. I did not like this book. This is the book I first learned complex analysis from. I hated it. Thankfully, the lectures were really good. I think part of it was that there was a lot of typos, which I guess I hate less now. It definitely sucks a lot when you're first learning the field, but I've also come to, as I mentioned in my in my video about Bump's book on automorphic forms, in a certain sense, I can appreciate typos as an exercise to go and find them. But it's certainly annoying for beginners. I wonder if I feel different about this book now, though, if I went back and looked through it. There's some nice pictures. Any intro to complex analysis book should contain many pretty pictures, and in fact, this probably contains more than others. To be perfectly honest, like just flipping to some random pages and seeing those pretty pictures that are there, right? So, yeah, maybe this is worth revisiting. Let's go through the table of contents as is standard for some of these reviews. So, it's a pretty standard course. Talking about complex plane, ways of representing different complex numbers, continuity, paths, limits. Limits are now more complicated. Power series, which is nicer actually. Differentiation, exponentiation, integration. I mean, all pretty standard stuff. I'm not. I'm not sure I have all that much to say about it. Taylor series, Laurent series, residues, and even a little bit of conformal transformations and analytic continuation stuff. So I mean pretty standard course, and Ian Stewart, I think, has some good books. Like, I remember when I first took algebraic number theory, I supplemented some of it with one of his books. Which, I also had mixed feelings about. I thought some of his explanations were really good. But others just didn't quite appeal to me. I don't know, I guess I wasn't buying the proofs or something. Something like that. I don't even remember. It's been a while, actually. Wow. Well, I said this was going to be a great review of a bunch of interesting books. That's still true, but here's one I haven't even really read. Here's another one I haven't even really read. Another one I picked up for free somewhere along the way. Lectures on Morse Homology. Apparently, this is a pretty difficult subject, and I don't think... Oh, wait, no. I must have bought this, actually. I know the bookstore I bought this at. I think... here's another book that actually maybe I should revisit at some point. Because this is, Morse homology sort of has a reputation for being difficult. But I wonder if I would, if I have the mathematical maturity to really appreciate it now. Or it might be a flower homology theories, I think particularly are known to be difficult, if I'm recalling correctly. But, we've got some stuff about, it's focused around manifold theory, and sort of Morse functions, which I think help you, pick out singular points or something like that. Some sort of point counting stuff is involved anyways. Like I said, I've not spent a lot of time with this book. Homology theory, and I guess by the time we're over here, beyond the basic differential geometry, I'm kind of at a loss for what's even going on. I haven't even opened this book for a long time. So, I guess let me know if you want to know more about this book, because I don't have a lot to say. But here's one absolute banger. I mean, timeless classic, legendary book. If you know algebra at all, you know Atiyah-Macdonald, right? It's just no one even mentions the title of this book, right? They just say Atiyah-Macdonald. This course will use Atiyah-Macdonald. The results in Atiyah-Macdonald. There's other books on my shelf that we'll talk about that have a lot of more modern perspectives on algebra and maybe nicer typesetting, whatever, more comprehensive. But this book holds up. It's nice. It's got nice sets of exercises, nice detailed explanations, and it's often, people who are saying like, oh, I'm interested in getting into algebraic geometry. What do I need to know? People are often pointed to this book, and well, I think we'll see why in the very first chapter. right? So I just, I absolutely had to have this book on my shelf. Total classic. Yeah, I mean, the first chapter on rings and ideals, right? So you could view this as an introduction to ring theory. I mean, yeah, maybe not the easiest place for your absolute first introduction to rings, but if we jump over to the exercises on page 10, like some of these exercises are already setting you up to be thinking about schemes and like the spectrum of a ring, which, okay, maybe that scares you right away, but this is all really like just algebra. And then I think somewhere in one of these exercises, oh yeah, the prime spectrum of a ring, right? So right there on the exercise on page 12, we've got some exercises that introduce that to you. But it's not all, the super abstract category theory approach if you don't happen to like that. And you could skip that exercise and just treat this as a regular book on algebra, right? So some pretty succinct explanation of module theory, classic stuff, exact sequences, tensor products, and then, of course, this all gets related to how modules and categories of modules actually help us to understand rings, right? Rings and modules of fractions, also really big, right? Local properties, really big and important to be getting into, scheme theoretic algebraic geometry. I haven't spent as much time with the later half of this book. I mean, I've learned this material, but from other places. I sort of used the first couple chapters, and up, say, for example, here that going up, going down, theorems and valuation rings. Interspersed in other courses. Noetherian rings, of course, very important kind of flavor of ring, and maybe not mentioned as often in a typical sequence of algebra. At least the sequences of algebra that I've taken are their, sort of spiritual counterpart, Artin rings or Artinian modules versus Noetherian modules. And then, yeah, so, completions. That's really interesting to the theory of completions because, it's sort of an abstracted version of what you do to create the p-adic numbers, which is, a basic object of study in my research. And, but it does it from, this is a nice way of connecting the analytic bridge and the algebraic bridge, right? So this is a sort of like algebraic categorified construction that then they turn around and say, well, look, this is actually topological, and you can relate it to the normal topological definition of these sorts of completions, which is really nice. I like when different fields interact like that. So that's one of the biggest classics in algebra, still firing today. And I guess I could do 2 more books. Let's pack this one up. There's a couple other goodies on the shelf. Different math books serve different purposes, in my opinion. Some books are, like that one Green Langland's book I talked about. They serve as just sort of an overview. They're not meant to be studied from in depth and to like get a working knowledge of an area, but to more give you a bird's eye view. And the next book is kind of that, but for theta functions. So theta functions, they come up in a number of different ways. They definitely are related to like the theory of modular forms. And this is a nice sort of book. I think there's some proofs in it. There are some proofs, but it's definitely more of an overview of just a number of different ways that theta functions show up. So I mean, just look at this table of contents, right? Just boom, 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 right? And like all of these are, you know, just a page or two long explanation, right? But you can probably already see there's lots of interesting, right? Riemann hypothesis, oh, something about the heat equation, right? So we got, you know, there's number theory, there's differential equations going on, there's, you know, Mach theta functions, all these sorts of different interesting sorts of things, right? I think, you know, there's discussion of some of the combinatorics, you know, that pop up. So it really is just a whirlwind tour of theta functions, and a bunch of the different interesting ways that they show up. So yeah, I don't know if I would say like you go out and buy this skinny little book, but if it happens to be on your library's bookshelf, or you have a chance to grab a coffee, yeah, why not do it? It's a nice little overview. It's a nice little book to have on the shelf when maybe your brain's moving and you want to read some math, but you just can't hack a bunch of you're burnt out on excruciating detail for the day. Grab the book and a cup of tea and have a look at it. And then the last one is another one I've only visited here and there and sort of used it as a reference for certain parts, but it's a really nice book. Analysis, Manifolds, and Physics. So probably I would recommend this if you're into physics, mathematical physics, and maybe you need to bolster some of your mathematics in order to learn some more physics type stuff, right? So it's a cool book, and I guess for me, I don't know if I learned that much physics from it, actually. I mean, it's pretty oriented on the math side of things, right? But there's a lot of stuff in this book. It's absolutely fantastic. So, I mean, you start right from set theory, which is nice if you're a pretty big beginner, right? Sets, groups, rings, modules. Of course, you know, topology. Now, this is not a place to be, well, as it says at the top, right? Review of fundamental notions. So this is not a place to be learning any of these things, but it is nice if, especially if you're a beginner, not, you know, a mathematician proper. It is nice to have this notation set here, right? Topology, measure theory, even, and a little bit of functional analysis. Of course, you need that for quantum mechanics. So, speaking about quantum mechanics, well, even before that, right, there's stuff on, like, calculus of variations, right, that's important even in classical mechanics for, like, Lagrangian and Hamiltonian systems, for example. Then we've got, you know, an introduction to differentiable manifolds, finite dimensional case. Ooh, does that mean they talk about infinite dimensions? And yeah, look, all this interesting stuff, vector bundles, tensor bundles, groups of transformations, right? We're already getting into, like, Lie derivatives, Lie groups, integration on manifolds. So, you know, there's a lot of stuff like, you know, Gauss, Stokes theorem and all the stuff. A lot of stuff that's pretty, maybe classical to any treatment of like differential geometry, but maybe stuff like, I don't actually know much about characteristic systems, and, you know, symplectic Hamiltonian structures, you know, maybe less likely in other books that I love for differential geometry that I've mentioned, less likely you dive into those in detail, right? And then, I mean, of course, this is, you know, mathematics for physicists, right? So of course we're going to talk about Riemannian manifolds because we need that for general relativity. What else we got here? Distribution theory. Fourier transform, of course, that's everywhere and all over everything. Sobolev spaces. And yeah, I guess we don't even get into the math, right? Oh, speaking of Morse theory, call back to the, a couple books ago in this episode. And, at the very end, I mean, there is some stuff, right? So I guess we can see there's the Klein-Gordon equation, right? So it is peppered in here. That's right. I thought I did learn some physics from here. Right, I mean, flow of a vector field, of course, but mathematicians talk about that stuff too, so... but anyways, it's a nice reference book. I've definitely looked at it the odd time. There's some cool exercises in it and whatnot. And yeah, older book. I think it's from the 70s. Well, if you consider that older, but stands up. So I think that's basically gonna do it for this video then. Yeah, there's more good stuff on the way. More stuff. Next episode, we'll have more stuff that is my absolute favorite, and more stuff that I've barely read, and I'm excited about all of it. So, I'll see you then.